Okay, so we're going to look at a set of notes on what is called the least squares regression. Okay, so imagine that I have a scatter plot, and here's my data points. Yeah, so I got a bunch of data points there, right? And what I want to find is a line. Okay, so some line. So this is going to be in the form of y hat equals. So I want to make sure that my notation is consistent here. B sub 0 plus B sub 1 times x. Okay, so this is my x-axis, this is my y-axis. Each of these points has an x and a y value. And then what this line is a line that is a guess, right? It's a guess. So like, given a particular x value, sorry, let me pause that. Okay, so that was like really wild. I got like everything got a lot of focus there for a minute. So given a particular x value, right, I want a line that is going to predict the y value that's associated with that x value. Well, this line is not predicting this point very well. Okay, so the point here is x, y hat, and this is the point on that line that I am using to predict this value, okay? But like, if you look back here, like if I picked this x value, so we'll call this one x1, 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 we'll make this one x2, like, okay, so I go up here, right? The prediction for x2 is there, so this would be like y hat 2 for x2, and perhaps like this is the actual value, so this one's not off as bad. Okay, so what we call the distance between the prediction line and the actual data point, right? The distance between the prediction line and an actual data point, we call that a residual. Okay, so it is the predicted value. Sorry, no, got that backwards. It is the actual value minus the predicted value. Okay, so if I have my data point is below the line of prediction, right, the residual is going to be negative, right? So this one is going to have a negative residual. This data point happens to be above the predicted value, so its value is going to be positive. And each of these data points is giving me a different residual value. That one's positive, that one's negative, that one's negative, that one's negative, there's a positive, right? So a whole bunch of residuals. Okay, so what we're going to do is we're going to pick the line where if I take each of these residual values, right, so we'll call those residual values the y sub I minus y hat sub I, right? I'm going to take each of those residual values and I'm going to square them. Why am I squaring them? Because I don't want the negative ones to cancel out the positive ones, right? So I'm going to make them all positive. And the way I'm going to do the positiving there is I'm going to square them, and then I'm going to add those all up. So what I want to do is I want to find the line that minimizes those residual values, okay? So another way of saying this is I want to find the line that finds the least of the sum of the squares of the residual values. So this is what we call the least squares regression line. Okay, so this is where this weird term comes from, the least squares regression line. Now, one of the nice things is that your calculator actually does this for you. Okay, so if you have a data set in your calculator, and we're going to see this in class, it will actually come up with the regression line for you. Now, let me bring up a new picture and kind of talk about some of the limitations of this. So let's just say I have a very small data set, right? And I have like a point here, and a point there, and a point there, and a point there. Like 4 points in my data set. All right, and then I draw what I think is the least squares regression line that kind of runs through these. Might look something like that. Okay. And this is hopefully the thing that minimized these residuals. Okay, so the key here is that my data is running from, let's say, x1 to x4 for my explanatory variable, right? And this is my response variable, right? And it's giving me a way to get an estimate on that response variable. So y is b sub 0 plus b1 times x, right? That's my least squares line. So where is this line most useful? Well, it's useful in like making predictions over the interval of the data. Okay, and we actually refer to that as interpolation. Is that like if I use the line, like let's say I had x star here, and I want to make a prediction as to what would be the response variable for x star, I would choose that point, and I've made an interpolation. Okay. Once I get beyond the set of the data that I used to make the least squares line, so like if I'm out here or out here, so actually let me erase those and put those in like red. Okay, if I'm out here, way above or way below the data set, then I am into what is a practice called extrapolating. And I'm putting this in red because this is dangerous. Okay, you're running a risk here because like so long as I'm on the interval of interest here between like the lowest point of data and the highest point of data, I'm pretty safe in my predictions. Okay, if I get out here, I have no idea whether or not this line is going to hold once I get out of where I've taken data from. So we're getting into this process called extrapolating. I'm going to say that this is dangerous because this is likely to lead to bad conclusions or bad guesses. Okay, so we want to avoid extrapolating as much as possible. So if we're going to use the line of best fit to make some sort of prediction, we want to kind of limit ourselves to being like within the data set or maybe just a little bit beyond that. But if I get way beyond that, I'm getting into some pretty dangerous territory. So this is going to lead me to something that's called the coefficient of determination. So let's talk about that. Okay, so when we were talking about association and correlation, we got a correlation coefficient, right? And we called that R. And we said that if R was less than 0, we were negatively correlated, or we had negative association, association. If R was greater than 0, we had positive association. If we were close to 1 or negative 1, we had strong association of two variables. And if we were near 0, we had weak association of two variables. And this thing is restricted between negative 1 and 1 inclusive. Oops, R should be in the middle there. R is restricted between negative 1 and 1 inclusive. All right, so happens that if I do and I take the square of that value, r squared, I get what we call a coefficient, coefish, IC, there we go, ICIENT, there we go, of determination. Okay, so the coefficient of determination specifically applies to this line. The y hat is equal to b0 plus b1 times x. Okay? And the question is like how strong does this predict, right? It's kind of like, how strong does this predict? Or in other words, how determined by x is y? Okay, so like this, when it's true, is saying that y is strongly determined by x. If I take x and I multiply it by a particular number and add another number to it, I'm going to get y. And it's kind of like, kinda, but then I get these residuals, right? So r squared, which is taking this correlation coefficient that we got in the last unit and squaring it, actually tells me the percentage of the change in y that is explained by a change in x. So how much of a change in the response variable is explained by a change in the explanatory variable? Okay, so what percentage of the change in the response variable is explained by a change in the explanatory variable? So if r squared is really close to 1, 100% of the change in the response is explained by a change in the explanatory variable, which basically says that given this model, I can completely guess correctly the value of y given x. I just have to multiply x by the right thing and add something else to it, and I'm going to get y. Now, not everything works that way, right? So there's going to be a certain point where I'm looking at my scatter plot, and some of the change in the y can be determined by the x, but not all of it. Okay, so like if I have an r of 0.98, then I would say 98% of the changes in the y's are determined by the changes in the x. If I'm down like 0.25, I would say 1/4 of the change in the y can be explained by the change in the x variable. 0 means these things are completely not correlated at all, right? And it's just like above, 0 has a sense of no association. So basically, you calculate this number the same way you do r. You just take that r value and you square it. Now, why is this useful? Because if I have a high r, then I know that my model predicts very well. If I have a low r, then high r being close to 1, my model, or r squared rather, I know my model is going to predict very well. If I have a low r, which is close to 0, I know that my model is pretty close to junk. Okay? Now, most things in the world are not explained by a single explanatory variable. Okay, so like right now we're keeping things pretty simple, and we're using one explanatory variable for the response variable, and that gets me an r squared. A little bit later in like possibly collegiate statistics, you might get into something where you have like multiple explanatory variables, 2, 3, 4 different explanatory variables for a single response, and you can parse out which one of those is contributing how much to being able to explain the reality. So, and then you could say, well, if I take all 4 of them together, now how good am I getting at predicting things, right? So r squared kind of expands beyond the situation that we're given here. But for our sake, we're just going to use this as how well does this single explanatory variable, what percentage of the change in the response variable is explained by our explanatory variable. Now, there's some interesting things here where I can actually calculate r and r squared without actually knowing the whole data set. If I know some sense of some summary data about that set. So let me show you some of that reality here. I'm sorry, I messed that up. I said that you could calculate r and r squared. That's not correct. You can calculate the parameters of the line of the least squared regression line. So remember, my least squared regression line here is a y hat is equal to b0 plus b1 times the explanatory variable. So this is like, typically we would have called that the slope and the y-intercept. And I can get these just from the data of the problem and be able to pull this off. So the first one that I can get is b1. Now remember, r could be calculated without this, right? Because we had that r was 1 over n minus 1, right, times the sum of the x values, right, over their standard deviation times the y values, right, the difference between the value and its mean over their standard deviation, right? So this is something that I could completely pull just from the data set. So b1 is actually r times the standard deviation of y over the standard deviation of x. So if I actually know the data set, I can get, if I know all the x values and I know all the y values, right, I can get the mean of the x values, I can get the mean of the y values, I can find the standard deviation of the x values, I can find the standard deviation of the y values, right? And then what can I do? I can take 1 over n minus 1, take the sum of that, multiply all of these out, get r, and then take sy over sx, and this will give me the b value for that line. Well, that's kind of nice. And then the other one that I can do is I can get the b sub 0. So the b sub 0 just says take the mean of the y values, and subtract that b1 that I just calculated, and multiply that by the mean of the x values. Okay. So if you kind of look at this last sentence, this is kind of interesting, because if I move things around a little bit here, right, and I bring the y bar over by itself, right, bring y bar over by itself, that means b sub 0 stays positive, and the b1 becomes now positive. Another way of saying this is that the mean of the y values is equal to b sub 0 plus b sub 1 times the mean of the x values. So the AP exam plays around with these two formulas a little bit. That one, and sometimes they revision it as this. So knowing these is probably pretty useful coming into the exam when you're talking about two variable statistical analysis here. So we're going to do some work with these least square regressions. The first thing I'm going to do is show you how to use the calculator given two data sets to, or paired data to get them, and then how you see the r squared, and kind of questions that would come up on the test about this. All right, so we'll see you soon in class. Thank you.